You know those intricate, repeating patterns you see on all kinds of fabric? Ever wonder how they're made? Well, it's not magic, it's all mechanics. And for a huge range of the fabrics we use every single day, the secret is a brilliant piece of 19th century engineering that solved a massive manufacturing puzzle. The answer? A surprisingly clever device that's part machine and, believe it or not, part computer, the Dobby loom. So, here's the plan. First, we're going to unpack the weaver's dilemma. Then, we'll meet our hero, the Dobby, and get right into how it works. We'll watch a classic design in action, meet some of its cousins, and then, and this is the really cool part, we'll discover its incredible legacy as one of the world's very first computer programs, written not in code, but in wooden pegs.
Okay, so to really appreciate just how clever the Dobby is, you have to understand the problem it was built to solve. Back in the day, weavers were kind of stuck between a rock and a hard place when it came to making patterns.
On one end of the spectrum, you had your tappet looms. Now these are workhorses, great for basic stuff like plain cloth or simple stripes, but they're really limited. You're not making anything fancy on them. Then on the other extreme, you had the jacquard loom, an absolute marvel, capable of weaving massive, complicated pictures, almost like a fabric printer. The problem was, what if you wanted something in the middle? You know, something more interesting than a simple stripe, but not a full-on tapestry. That was the gap. That was the challenge.
And this is where our solution comes in, the Dobby mechanism. It was the perfect middle ground, hitting that sweet spot the textile industry was desperate for. It allowed for small, geometric repeating figures that were just complex enough to be beautiful and interesting.
So what is it exactly? Well, a Dobby is officially a shedding device, and that just means its job is to create an opening, or a shed, in the main threads. It does this by very precisely lifting and lowering sets of threads using these frames called heels. By controlling way more heels than a simple loom, it could suddenly weave in all these cool, repeating figured patterns.
And here's where it gets really good. A Dobby can typically control anywhere from 6 all the way up to 48 shafts. Now that is a massive leap in power from a basic loom. It gave weavers the freedom to create a huge variety of patterns without needing a giant, complex, and expensive jacquard system.
Now you might be thinking, okay, a Dobby is a Dobby, right? Well, not exactly. Engineers came up with all sorts of different designs depending on what they needed the loom to do. And looking at how they're classified really shows you how they tweaked and perfected the technology for more speed, better efficiency, and just finer control over the fabric. They're mostly broken down by how they lift the threads, how they control the movement of those threads, and the type of opening or shed that they make for the shuttle to fly through. And yeah, there are even super specialized versions for very specific jobs.
Let's look at the biggest difference, single lift versus double lift. The early single lift Dobbies were pretty slow, and they were really tough on the yarn because they had to bring every single thread back to the middle after each pass. But the double lift design, that was a total game changer. It could run way faster with a lot less stress on the yarn, all because it could hold some threads up while moving others. This created what's called an open shed, and this is the design that really took over the industry.
Okay, theory is great, but how does this thing actually work? Let's get our hands dirty and see these principles in action by taking a look inside a classic double lift design, the Hattersley Dobby. I know this diagram looks a little intimidating, but the idea behind it is actually beautiful and simple. The key players here are that rocking T-lever at the top, 2 moving knives labeled D and E, and 2 sets of hooks, P and Q. These parts all dance together to turn a pattern into threads being lifted up and down. The whole show starts down at the bottom. There's a pattern barrel, we'll get to that in a bit, that tells a specific hook, P, what to do. If the pattern says lift, that hook drops down and latches right onto the moving knife D. Okay, next up, as the whole loom turns, that big T-lever pivots. The knife, D, slides across, pulling the hook it just captured along for the ride. And that one simple movement sets off a chain reaction through all the other levers, which yanks up the heel frame, L, at the bottom. And just like that, a specific set of threads has been lifted, and our pattern has begun. And this, right here, shows you the genius of the open shed. That thread stays lifted. It doesn't drop back down. In the meantime, the other set of hooks and knives, Q and E, are already moving into place, getting ready for the very next instruction from the pattern. This constant overlapping motion is what makes the double lift Dobby so incredibly fast and efficient. How clever is that?
So the Hattersley is a classic for sure, but it's just one branch on a much bigger family tree. As the world of weaving changed, engineers kept inventing new kinds of Dobbies, each one a clever answer to a new problem.
Just look at the difference. On the left, you've got the hook and knife system we just saw. But on the right, you've got a rotary positive Dobby. That thing uses these incredible gears to give the weaver total control over both the up and the down motion of the threads. That's absolutely essential if you're working with really heavy or tricky fabrics.
Or check out this specialized machine, the cross-border Dobby. This thing uses multiple pattern chains, one for the main part of the fabric and another one just for the border. It can automatically switch between them, weaving the body of, say, a towel or a tablecloth, and then perfectly execute a complex border. Just brilliant.
And this, for me, is where the story goes from being about clever engineering to something truly mind-blowing. Remember that pattern barrel we mentioned? It's way more than just a part of a machine. It's actually one of the very first forms of stored, programmable information.
The pattern is literally encoded onto these wooden bars, which are called lags, and it's a pure binary system. A peg in a hole is a 1. It tells a lever to grab a hook and lift a thread. A blank space is a 0. It does nothing, the thread stays put. A chain of these lags is, for all intents and purposes, a computer program for weaving fabric.
Of course, wooden pegs wear out. They break. So the next step in the evolution was to switch from wooden lags to punched paper cards, made by a machine just like this one. Not only were the cards more durable, but this drew a direct line from the textile mill to the birth of modern computing and the punch cards that ran the very first computers.
So, you see, the Dobby loom is so much more than a machine for making patterns. It's a monument to mechanical programming. And that leaves us with one last thought. If a simple system of pegs and holes could automate something as complex as weaving over 150 years ago, what simple, elegant ideas may be hiding in plain sight today are writing the programs for the technologies of tomorrow?